Welcome to the next video in the mathematical logic sequence. In chapter 2, we're now talking about homomorphisms. So to get started with an informal presentation, just imagine, or the whole thing is about basically trying to take some two structures that may at first glance seem different because they give different things different names, and yet to find that actually they behave in exactly the same way, or if not exactly the same way, then something close to it. So anyway, just to take as an example, imagine that you had a structure where the domain has a single element and no function, no relation, no constant. And you had some other structure with a domain containing a single element and likewise no other operations or whatever. So the language itself must have no extra logical symbols in this example. Well, then really the only thing is that each one has like a single element in its domain, but because the domain just has a single element in it, then in some sense it just seems like they're basically the same, right? You can kind of say the same things in logic about this one element in either case, so that in some sense they're kind of just the same structure, just you call the elements different names, but if all you do is you call them different names, then it shouldn't really make it a different structure. Or, you know, like if you had, for instance, if you had a structure, for instance, where the domain was the numbers 1 to 26, and you define sort of operations on these numbers and relations and so on. And then you had some other structure where the domain was the letters A through Z, and you define operations and functions and relations on these things. But there's, right, kind of what you do to the numbers, the way that the functions and the relations act on the numbers is actually the same way that the letters relate to each other in the other structure. Well, then they're basically the same structure. Again, you're just choosing to call the elements by different names, but that shouldn't matter. They're sort of spiritually the same structure. So that's what the idea of a homomorphism is attempting to capture, is this idea that sometimes two things can be called different names, but they structurally are basically the same. Now, slightly more technically, the way that we're going to try to capture the idea or whether some two structures have a homomorphism between them, which is to basically say that there's some kind of identification of the things in one structure with some of the things in the other structure, is that we're going to get a map from the domain of the first structure to the domain of the other structure. And what we want, right, like for the structures to sort of behave the same way, is that if there's any kind of relationship among the elements before the mapping, so to speak, which is to say just in the domain, in that first structure, then the same sorts of relations should also should hold among the things after you perform the mapping. That is to say, between the same elements that are being assigned to each other through this mapping from A to B. So stuff that happens before the mapping should also happen after the mapping. That's the informal presentation. Formally, what this means is that if you take any constant in your language and if you interpret it in A, then this mapping should assign it the same thing as if you were to interpret it in B, right? So that's a kind of, you know, this is what you have before the mapping, and you get the same thing after the mapping. So that's kind of a demonstration of what we're talking about, right? Trying to sort of show how this formalization is making good on the informal description. And then we have a similar kind of description of what should happen with the relations, right? So this, you know, if you have this holding before the mapping, then whatever you assign A to, right, this is after the mapping, you should get the same relationship according to the other structure on the same symbol. And then we have another one for the function symbol and so on. Now we can very quickly define some other familiar definitions if you've seen any sort of abstract algebra or similar content. Right, if you have a homomorphism, which is a bijection, then we call it an isomorphism. If you have an isomorphism from a structure to itself, then we call that an automorphism.